So here we are finally at area between two curves, and you kind of see that there are, two classic pictures here, and we're going to use both of these strategies, the idea of vertical rectangles versus the idea of horizontal rectangles. And so it depends on, the shape of what you have, or, how this region comes together, which one you're going to use. And really the first version is the one that most people are most comfortable with. It's y as a function of x, which is what you studied in an advanced algebra class and pre-calculus. You have not studied x as a function of y like we have going on in this example. So I guess over here, I could call, f of x, you're allowed to call that as y. You've had a lot of experience with that. I could even, use a subscript and say, hey, this is y sub 1, because I have two graphs, I have two functions. Y is a function of x. I'm going to call that one in blue there, y sub 1. And the one down here in red, I'll call that y sub 2. Right, I have two functions. That's function g as a function of x, right? So let's just start with the vertical rectangles. This is what you guys have experienced a lot in the past in your previous math classes. And what I'm going to do in the shaded region, we're trying to, our goal is to find the area between these two curves from A to B. And so what I'm going to do is draw a rectangle in the shaded region. Right, here it is. I'm going to draw all these rectangles, and really just kind of remembering that when I'm doing area, it's the integral of the height and the width. So in this case, if I wanted to say how long this is, I would say, well, let's just subtract these. If I just could say hey, this guy has a y value of 8, and I'm just making this up, and this guy has a y value of 3, I would say the length there is 5. 8 minus 3 gives you 5. So I'm certainly not saying those were the real numbers, but that's how you would get the length there of this rectangle, is I would say okay, let's handle this the same way we would a Riemann sum, right? I want to kind of find the area, and I want to get the area of these little rectangles by multiplying the height times the width. Okay, and I'm going to say, but I really want that width to go to 0. Right? This is what's going to give you the area that we're looking at, the area between those two curves. And now, when you see a limit as the width goes to 0, up against that sigma, that's what kind of merges together and gives you that integral sign. So again, the height here is really f of x minus g of x. It's top minus bottom. So I can write it as y1 minus y2, just because I use those subscripts. Now again, this little width is some kind of delta x in here, this kind of space along there. We're just going to call it dx, because again, we're sort of making that width go to 0. So here's my general definite integral. I'm going to go from a to b. That's my start and stop. And I'll go ahead and put those function values in. This is what you see in a lot of calc textbooks, right? Area between two curves is f of x minus g of x. Now, I need you to be careful about that, because if g was higher than f, it would be g of x minus f of x. So instead of thinking about it like this, which you will see in your textbook, no doubt about it, I usually do something like this, where I say, look, if you drew a vertical rectangle, I even put a vertical rectangle next to it, then the area between those curves is going to be top minus bottom. And I'm also going to point out that that little dx there on the end is a pretty powerful statement. That's what tells you, hey, look on the x-axis to find your start and stop values, to find your limits of integration. So this is really what I want you to latch onto for what should I be studying, or what should I be using to set up area between two curves. If you drew your rectangle vertically, then you're going to say the integral of the top function minus the bottom function dx. And again, look on the x-axis to find those limits of integration. If you have the different perspective, now this is different. You have not really discussed a lot of functions of y. That would be x as a function of y. So I can sort of describe this and say, well, let's use the idea of subscripts. Let's say x1 is f as a function of y, and let's say x2 is g as a function of y. It would not make sense to do a vertical presentation here with these two different functions, right? This one here is is x sub 1, x is a function of y, and this guy over here on the left is this x sub 2. It's just a different perspective, same idea. I still want to say, hey, we're looking for area, and in order to do that, what I'd really like to do is just sum up, again, I'm going to kind of make the widths go to 0 of height times width. Okay, so here, if I think about, again, I'm going to kind of imagine, like, there's my little rectangle that you're going to draw in. You're going to draw in whatever you can, and here are my endpoints. See, I'm touching each one of those curves. And so from there, then I'm going to figure out, well, if I think about this rectangle, what would the area? Well, this distance across would be your height. And again, just putting numbers in here, if this had an x value of 5 and that had an x value of 1, you would say the distance would be 5 minus 1. You'd say it's 4 units long, right? It's always right minus left. You always want a positive value for the height of that rectangle. And so, again, I'm not saying that's really 5 and 1. I just made it up. But I want to sort of get to this idea of like, well, I'm going to take this x coordinate and subtract that x coordinate. That's how you would get the length of that rectangle, right? So I am going to switch this into a definite integral. Whenever you see that limit as the width goes to 0 up against that sigma, it sort of transforms into that integral sign. And here I'm going to say, well, I'll just do x sub 1 minus x sub 2, but it's dy this time. Your width, if I can show you, it's along the y-axis. That's a little change in y value. So we're going to kind of translate that into our definite integral as a dy, which is a very powerful statement because that little dy is what tells you, hey, where are you supposed to look to find your limits of integration? Well, they're y values. So you have to look on the y-axis. So here's my lowest y value of what starts building this area. I'm going to call that y equals c. And then, slide over here. And then over here, that's the stopping point on building this area. I'm just going to call that D. So what you're saying is I have all these rectangles that are really, really skinny and thin, and we're going to start building at y equals c, and we're not going to stop until we get all the way to y equals d. Okay, so now again, instead of saying x1 minus x2 or f of y minus g of y, I mean, essentially that's what it is. What I want you to view this as, no joke, is, hey, the right function minus the left function. That's what I want you to see. Because depending on the labels, maybe they'll be backwards, and I don't want you to be in a bad situation because of that. So I'm going to transfer this over and say, look, what I want you to know is that if you're doing something on a horizontal presentation, you're going to set up right minus left dy, and then again, that dy is a powerful statement where you look on the y-axis now for your limits of integration. Okay, that's where you start building your area, and then you stop. Okay, just like over here in the vertical presentation, if you start at x equals a with these vertical rectangles, you start with a rectangle at a, and you keep doing all of these rectangles all the way through the shaded region until you stop at x equals b. Okay, so these are the two versions I want you to know for area. I'm even going to draw, like I said, I'm even going to draw a little horizontal rectangle over here to indicate that. So these are the things I really want you to remember to think about area between two curves. Okay, so we're going to do two examples. We'll do a lot, but we'll do a few examples here, and then split it up a little bit. So look, this class is no calculator. It's designed as such. You should be able to sketch these functions without needing the use of a graphing calculator. And so that's what's going on here with this example. Okay, so I guess I have these misnumbered, but example 5. We're going to sketch the region bounded by this parabola, right, and this line, this horizontal line. So I'm going to draw those two things because I really think these are two separate questions. First, we got to sketch the region, then we'll figure out setting up that integral. To me, it's sort of like two problems here. So I'm going to sketch them. I'm not going to be like crazy about it. I will say this is a parabola that opens down because it's got a negative in front of the x squared. And you know, one of the easy ways of kind of recognizing what some of the key points of this graph, in this case, I think is just factor out an x. you can get your x-intercepts really quickly. Like I know when x equals 0 and when x equals 4, like the solutions to this equation, basically you're setting y equal to 0, you're looking for x-intercepts. I know that the x-intercepts are 0 and 4. And again, I'm going to marry that with, I know it's a shape of a parabola, I know it opens down, and so I can work on that. So I'm going to do my best to draw something as to scale as possible. Here's x equals 0. There's x equals 4, right? And I'm going to draw a parabola. The vertex should be right in the middle, and if I kind of try to be really good, that would mean f of 2 would be 4. That's pretty exact for me. Here's my parabola. Got it. Now I'm going to draw the line, well, y equals 3. That's just a horizontal line. I can see that on my graph because I actually have something drawn to scale. There's y equals 3. And so I have this shaded region in between. So let me just sort of color that in. I'm trying to find the area in there. So at least I have an image now of the area that I'm looking for. I want an integral to set this up. And a vertical presentation is going to look really good here. It's going to be consistent, which is what we're always looking for. Consistent meaning if I draw a rectangle anywhere in this shaded region, there is nothing special about the exact location that I happen to just put it in right there, that it is going to be the same. Top function is always on the parabola and the bottom function is always on the line. Just imagine sliding that rectangle a little bit on the left, a little bit on the right. It stays consistent, the top minus bottom. So I'm going to write that and say, look, I'm going to do the area. It's a top minus bottom because a vertical rectangle is consistent through that shaded region. So now let's fill in the pieces and say like, well, I have my top function is the parabola, right? So let me fill that in, 4x minus x squared. And my bottom function is y equals 3, right? Top function minus the bottom function. And I'm just going to kind of put that in parentheses here and say, okay, I'm going to slap a dx on it, which leads me to what are my limits of integration, of course, right? So I need to kind of think about that and think, okay, where am I going to go to get that information? These should be x values for your lower and upper limit of integration. And let's go back to our image. Here's the leftmost point of that shaded region. And here's the rightmost point. And I need to know, like, what are they? They're not given to me. I have to go searching for them. They're the intersection points of the parabola and the line. So I have to kind of go fishing and solve it out. So I'm going to find the intersection points the same way you did in your advanced algebra or pre-calculus class. I'm going to set those two equations equal to each other, and I'm going to solve this polynomial equation. And it turns out my solutions here are 3 and 1, which actually makes sense on my graph. I mean, I know my graph isn't amazingly to scale, but I can kind of reasonably say, like, oh, here they are, 1 to 3. Now I've got a really good definite integral that represents the area that I was charged with finding. So if it just said, hey, set up an integral, this looks great. Now, if I want to actually evaluate it, well, sure, let's actually evaluate that definite integral. And so you don't have to rearrange them, but I just usually like to get rid of those extra parentheses and go for it. Find that antiderivative. Oop, that should have been an x. So let me go back here and change that. Oop. So the antiderivative of 4x would be 2x squared. I got sidetracked. The antiderivative of -3 is -3x. All right, here we go. I got it down. That's my antiderivative. I'm going to evaluate first at 3 and then at 1, and we'll get that nailed down. So if I plug in a 3, there's that. I plug in a 1. Just barely squeaking that in. Let me move this over a smidge. And then I'll get to work on this. So let's see. That's going to be 18. 27 divided by 3 is 9. Minus 9. So that's kind of weird. This whole thing is 0, which is kind of strange. Over here, whatever it is, 2 minus 1/3 plus 3. So what does that give me? 2 minus 1/3. Oh, that's a minus 3. I'm going to pay attention here. And so let's see. I have negative 2 plus 1/3 plus 3. So that means I have 1 and 1/3, which is 4/3. That's the value of the shaded region between these two curves. Okay. So that's all your mechanics in there, right? As far as an integral that sets up the area, you were done right here. We're crunching the numbers, you know, doing the fundamental theorem. My final answer there is 4/3. Okay. Can zone out a little bit. All right, and let's take a look at this next example here, which is super uncomfortable because you haven't really had a lot of experience graphing you know, x as a function of y. This is a function of y. So the same way that you can replace f of x with y equals, I can replace f of y with x equals. I'm going to do that. And you can graph this however you want to, but I'm going to try to stay in your comfort zone here. Like, you're used to graphing y as a function of x. This is one that you can sort of handle in that way. Let's just solve this equation for y. Let me add 3 to both sides. Let's go ahead and multiply by 2. And let's take the square root. So I'm going to be graphing 2 different functions of x. See that? Like when you take a square root, you have positive and negative. Those are 2 different functions that are going to be on the same graph. So let's go ahead and graph those. And I'm going to graph them in different colors. I'm going to graph the positive square root in orange, and I'll graph the negative square root in purple. Okay, so let's set up a grid. Now it's a square root. The beginning of the domain is at -3. And I'm just going to kind of draw a square root function. In orange would be the positive square root function. That means all your outputs, all your y values are positive. And the negative in front means all your outputs are negative. See how that comes together? And really this is a sideways parabola. So you definitely handled this in an advanced algebra or a pre-calculus class, but I'm sure it's been a while. Okay, now if I want to take a look at this other graph over here, again, g of y, well, I'm going to replace that with x. This one's a little bit friendlier to kind of rearrange this to say y equals. All I have to do is subtract the 1, and I'm good, right? So there it is. And then from here, I'm gonna go ahead and graph this. We can certainly graph x minus 1, a linear function there. So I'll do that. This is going to be -√6. So here's where minus 1 would be, and I'll just draw that slope of 1. Oops. So I've got my shaded region here. I'm just going to kind of shade it in. And if I look at this, it's problematic to do this one vertically with a top minus bottom. When you think about it, I was given 2 functions of y. That's it, 2 equations. And to do this vertically, you can. It's really messy. So what I'm going to do is change my brain over and say, well, look, I was given 2 equations. How do I get this to work out as a function of y? And a lot of times when you're given a function of y, it is going to be this horizontal presentation. So let me draw a horizontal rectangle in the space, and you can see how consistent and awesome it is. Where if I draw a rectangle in horizontally, this is consistently the same. There is nothing special about where I happen to draw this little rectangle in my shaded region. The linear part, that function, is the right function no matter what, no matter if you slide it up or you slide it down. This endpoint is always going to be on the line, and this endpoint is always going to be on that sideways parabola. So remember, this is your sideways parabola. You're very consistent here through this process. So I'm going to set up the area with this right minus left idea because it works so well. So I'm going to set that up and say, okay, well, I'm going to have my right function minus my left function, dy, of course. And so what the right function is, now I'm replacing this. It's really going to be this function. This is your g of y function, and this is your f of y function. So it kind of looks like this. But again, I don't want you to like get stuck with like g of y and f of y and memorize that. I really want you to kind of get started with this right minus left, but I'm just putting those in so I know which one is which. I know g of y is the linear part, where I'm going to replace g of y with y plus 1, and f of y I'm going to replace with, well, 1/2 y squared minus 3. Now, once again, I have this issue of like, well, that dy on the end tells me two things, actually. It tells you that your integrand should all be in the y variable, which it is, so that's great. It also tells you that, look, your limits of integration have to come from the y-axis. So that means, okay, what's that y value right there? And this intersection point right here, where that line and sideways parabola meet, well, what's that y equals intersection point as well? So lucky for me, I'm going to handle this in the same way that I did the last example. You can use your algebraic skills to do this. Set the two equations equal to each other. That's how you find intersection points. And we're going to go ahead and do it. 1/2 y squared minus 3 equals y plus 1. Let's bring everything over to one side. I agree. I don't feel like dealing with fractions either. So I'm going to multiply everybody by 2. And then I can solve this with a really quick factoring and end up with my two limits of integration. The lowest y value you have is -2. I'm going to put that on my definite integral. And the highest y value you have is 4. So it's the same process, right? And it's quirky because, you have x as a function of y, which is interesting. But here is my definite integral that represents this area. This is, if I said set up an integral that represents area, this is great. You wouldn't have to do anything else on this to get it to work. And I'm not going to go through the work right here because I'm already at over 20 minutes here. But you can sort of, clean up your integrands a little bit, right? Have y. This is going to be plus 1, but then plus 3, so I might as well change that to a plus 4, and then the -1/2 y squared. It's worth it to kind of clean up those like terms. But I encourage you, like, actually crunch the numbers. Do this definite integral. It's not terrifying, right? It's just a polynomial. You should end up with the answer of 18. That's the area of the shaded region that you just filled in.